Our planet Earth is a dynamic and ever-changing place. While it may seem solid beneath our feet, the Earth's outer layer, the lithosphere, is broken into gigantic pieces called tectonic plates. These plates are in constant motion, albeit extremely slow. This movement, known as plate tectonics, is the driving force behind earthquakes, volcanoes, and the formation of mountain ranges. Imagine a jigsaw puzzle where the pieces are always shifting, colliding, and pulling apart. That's a simplified way to picture plate tectonics. The continents, which we perceive as permanent fixtures, are actually passengers on these moving plates, drifting across the Earth's surface over millions of years. The boundaries between these plates are where the real action happens. There are three main types of plate boundaries: divergent, convergent, and transform boundaries. At divergent boundaries, plates move apart, allowing magma to rise from the Earth's mantle and create new crust. Transform boundaries see plates sliding past each other horizontally, leading to earthquakes. But it's at convergent boundaries where the most dramatic changes occur. Here, plates collide head-on, and the immense pressure can trigger powerful earthquakes and volcanic eruptions. It is at these convergent boundaries that continents collide, setting the stage for the formation of towering mountain ranges. Continental collisions are some of the most awe-inspiring events in Earth's history. They occur when two continental plates carrying land masses converge. Since continental crust is less dense than the underlying mantle, it resists subduction, the process of one plate sinking beneath another. Instead, the immense pressure from the colliding plates causes the land to buckle, fold, and uplift. Imagine two cars colliding head-on. The force of the impact crumples the front ends of both vehicles. Similarly, when continents collide, the edges of the continental plates deform and crumple. The Earth's crust is forced upwards, creating towering mountain ranges. The process of continental collision and mountain building is a slow and gradual one, unfolding over millions of years. As the plates continue to converge, the pressure intensifies and the mountains continue to grow higher. The Himalayas, the highest mountain range on Earth, are a testament to the incredible power of continental collision. Over billions of years, the Earth's continents have repeatedly collided and broken apart, forming supercontinents and then splitting again in a cycle that continues to this day. Roughly 300 million years ago, the continents we know today were joined together in the supercontinent Pangaea. Before Pangaea, other supercontinents existed, such as Rodinia, which formed about 1 billion years ago. These ancient landmasses were eventually ripped apart by the forces of plate tectonics, with new oceans forming between the separating continents. Looking into the future, scientists predict that the current continents will eventually come together again to form new supercontinents. One such hypothetical supercontinent is Pangaea Proxima, which is predicted to form in about 250 million years. Another possibility is Amasia, a supercontinent centered around the North Pole. These predictions are based on our understanding of plate tectonics and the current movements of the Earth's continents. While it's impossible to predict the future with absolute certainty, the cyclical nature of supercontinent formation suggests that the Earth's landmasses will once again coalesce in the distant future. The process of mountain building is influenced by a number of factors, including the rate of plate movement, the thickness of the continental crust, and the erosional forces that wear down mountains over time. The faster the plates collide, the more intense the pressure, and the faster mountains can grow. The thickness of the continental crust also plays a role. Thicker crust tends to be more buoyant and resists subduction, leading to more significant uplift and taller mountains. Conversely, thinner crust is more easily subducted, resulting in less dramatic mountain building. Erosion is a constant force working against mountain building. As soon as mountains rise, wind, water, and ice begin to wear them down. The rate of erosion depends on factors such as climate, rock type, and the steepness of the slopes. The interplay of these factors determines the ultimate height and shape of mountain ranges. For example, the Himalayas, located in a region with a high rate of plate convergence and thick continental crust, continue to grow in height despite ongoing erosion. In contrast, the Appalachian Mountains in eastern North America, formed by ancient collisions, have been significantly eroded over time and are now much lower in elevation. The dynamic nature of Earth's surface ensures that the process of mountain building will continue as long as plate tectonics is active. As continents continue their slow dance across the globe, colliding and breaking apart, new mountain ranges will rise, shaping the landscape for millions of years to come.